Welcome to K smallest amount with single denomination combination, LeetCode 3116. The question is, what is the K smallest amount you can make? You may use infinite coins of each denomination, but you cannot mix different denominations. Today we dry run examples, then solve it with binary search and inclusion-exclusion. The rule is simple. Coin 3 makes 3, 6, 9, 12, and so on. Coin 6 makes 6, 12, 18, and so on. You cannot mix 3 plus 6 as different coins to invent a new combo. Every valid amount is a multiple of one denomination. We take the union of all those multiples and find the K smallest. Example 1. Coins 3, 6, 9, and K equals 3. The unique amounts in order start 3, 6, 9, 12, 15. The first is 3, the second is 6, the third is 9. So the answer is 9. Shared values like 6 still count only once. Example 2. Coins 5 and 2, K equals 7. Merge multiples of 2 and multiples of 5, 2, 4, 5, 6, 8, 10, 12. The seventh value is 12. Answer 12. Key insight. Do not generate every amount. Binary search the answer X. For each candidate, count how many valid amounts are less than or equal to X. Find the smallest X whose count is at least K. The count only grows as X grows, so binary search works. Overlaps happen. 10 is a multiple of both 2 and 5. If we add floor of X over 2 plus floor of X over 5, we double count 10, 20, and so on. Fix it by subtracting floor of X over the least common multiple of 2 and 5, which is 10. That is inclusion-exclusion. For coins A, B, and C, count amounts less than or equal to X like this. Add floor X over A, over B, and over C. Subtract floors over pairwise least common multiples. Add back the triple least common multiple. Odd size subsets add, even size subsets subtract. Since n is at most 15, we enumerate all non-empty subsets with bit masks. Binary search finds the smallest X with count of X at least K. Search from low equals 1 to a large high bound. Take mid. If count of mid is less than K, move right. Low becomes mid plus 1. Otherwise, move left. High becomes mid. When the search ends, low is the answer. Algorithm steps. 1. Define count of X using inclusion-exclusion and least common multiples. 2. Binary search with low 1 and high about min coin times K. 3. While low is less than high, compute mid. 4. If count mid is less than K, raise low, else lower high. 5. Return low. Time is about 2 to the n times log of the range, which is fine because n is small. Here is the full Python solution. The helper count loops every non-empty bit mask, builds the least common multiple of that subset, then adds or subtracts X divided by that value based on subset size parity. Binary search calls count until low equals high. For coins 5 and 2 with K7, it returns 12. Zoom into count of X. For every non-empty bit mask of coins, build the least common multiple of the subset. If the subset size is odd, add X divided by that least common multiple. If even, subtract it. If the least common multiple already exceeds X, that subset contributes 0. This loop is inclusion-exclusion. Key takeaways. Valid amounts are multiples of a single denomination. Shared multiples count once. Binary search the K amount X. Count of X uses inclusion-exclusion with least common multiples. The smallest X with count at least K is the answer. N is at most 15, so 2 to the n bit masks are practical. That is K smallest amount with single denomination combination.